Okay, hi guys. So I'm carrying on with page 6 of the notes, and we're going to look at molar volume of gases. Okay, so Avogadro actually measured this and came up with it. So this is actually part of Avogadro's law. So all gases have this with the same number of molecules. Okay, so here you can see you got single atoms. So this could be something like neon, all right? Any one of the noble gases. These look like diatomic, so let's say it was oxygen, and these look like water. Okay, now remember this could be water vapor, so it's also a gas. So it says all gases will have the same number of molecules, okay, if they have the same volume under the same conditions of temperature and pressure. So what they are saying here is that if you have, say, 0 degrees Celsius, 0 degrees Celsius, 0 degrees Celsius, okay, so the same temperature and the same volume, you can see they're identical containers. Their volume is exactly the same, okay? So that means their volume is the same, their temperatures are the same, and it doesn't have to be 0, okay? I'm going to talk about 0 just now because it's over here, but it doesn't have to be 0. It could be 20 degrees, okay? It really doesn't matter as long as they're all the same and their volume is the same. It means that they would probably have, well, they will have the same number of molecules. Okay, so same volume, same number of molecules, same conditions of pressure and temperature. And you can see 1, 2, 3, 4, 5, 6 neons. 1, 2, 3, 4, 5, 6 oxygens. 1, 2, 3, 4, 5, 6 waters. Okay, so that is the law. It says here, 1 mole of any gas occupies the same volume at the same temperature and pressure. So now we've taken this and we say, okay, so if I have the same amount, okay, same number of moles, and I put it under the same temperature and pressure, their volumes would be the same. So let's say we actually had a full balloons, okay, with these 3 gases, okay. Let's say we filled balloons, okay, so they are our balloons, neon, oxygen, and water, okay. These are all gases. Okay, and they were at the same temperature, capital letter T, and they had the same number of moles. Okay, so the same amount. Therefore, all balloons would be the same size or volume. Okay, that's basically what it is. I'm sorry, I did all of that without you seeing. Okay, so oxygen, neon, and water in a balloon, if they were the same temperature and the same amount, so the same number of moles in each one of those, then all the balloons would be the same size or the same volume. Okay, that's basically what's been said here. Okay, so molar volume of a gas, it's a capital V with an M, okay? Now, this is the volume occupied by 1 mole of gas. So again, imagine these all contained 1 mole, okay? And we then did a same temperature and pressure, okay? And what we would find is this, okay? So the same, we would get the volume, okay? So it is the volume, so the size of these balloons, if they were filled with 1 mole, okay, all of them with 1 mole, okay, and if we put them under, or at a temperature of 0 degrees Celsius and under a pressure of 101 kPa, kilopascals, okay, they would all have a certain volume, right? And that is what's called molar volume. Okay, and I'm going to tell you now. Now, over here, okay, so, sorry, I'm jumping around. So it stands, what we're looking at is that it's a standard temperature and pressure, STP. Now these letters are very important. If you see STP, you can then use a special molar volume, because if the temperatures change or the pressure changes, the molar volume will change. Okay, but if you keep it at 0 degrees Celsius, so 273 Kelvin, or 1.01 times 10 to the 5 pascals, or 101 kilopascals. You can use either one. Okay, I think 101 kilopascals just makes sense. Okay, so STP is this temperature and is this pressure, and it's always those values if I say STP, standard temperature and pressure. And if we have 1 mole of gas, then your volume will automatically be 22,4. Okay, but be careful, because if I change the temperature, say I make all the gases the 20 degrees Celsius, okay, keep the pressures the same. So just like this scenario, say we had 1 mole, we're putting it at 20, and we have a certain pressure, but they all have the same pressure, same temperature, and 1 mole. Then their volumes are going to be different, their molar volumes. So when you see STP, you smile to yourself, because that means that you can use the 22,4. All right, if it doesn't say STP, you cannot use the 22,4. Okay, so, and also that means that if you have your constant temperature and pressure, and all your reactants and products are gases, you can then do a ratio, just looking at the ratio. So here we can see the numbers in the front. Now, so this is the first time that I'm referring to them as ratios, okay? So remember there's this 1 over here. So it's a 1 nitrogen molecule reacts with 3 hydrogen molecules to make 2 ammonia molecules. They're in a ratio, okay? And now we can say, well, because they are all gases, and let's say I say it's at STP, that means that 1 decimeter cubed will react with 3 decimeter cubes to give you 2 decimeter cubes of ammonia. Okay, the ratios of my balanced chemical equations work with decimeters and moles. Moles you can use anytime. Decimeters, you can only use it when it's all gases, or when there is a constant temperature and pressure. It doesn't have to be STP, but if there's constant temperature and pressure, you can then use that. Okay, so now you have another mole equation. Okay, so we can also work out moles this way. Volume, so the actual volume, like let's say this was 500 decimeters. 500, that's humongous, it's 500 liters. Let's say 0,5, half a liter. 0,5 decimeters cubed, okay? There's my volume. The molar volume I can now use, because I've said STP. They're at 0 degrees Celsius and 101 kPa, okay? And they all have 1 mole. Then I can use the 22,4. Please never just default to this equation just because you think you don't have anything else. The 22,4 can only be used when you have all gases and they have to be at STP. Okay, you can have constant temperature and pressure, but if it's not STP, you cannot use the 22,4. Then it is a different one. Okay, this is a constant and is on your data sheet. So a gas jar with a volume of 500 centimeters cubed. Now, here I've told you how to convert. You have to convert from centimeters to decimeters. Okay, it's from actually going from milliliters to liters. Okay, that's the difference. So centimeters cubed to decimeters cubed is dividing by 1,000. So here I have that. So this is 0,5 decimeters cubed. Right, now we're happy. A gas jar with volume 0,5 decimeters cubed is full of oxygen gas. Yay! At STP. How many moles of gas are there in the gas jar? Now we can use this. We've got a volume, and you know it's volume because it's decimeters cubed. And we have STP, which is 22,4, which is our molar volume. Okay, sorry, let me write the formula over here so that you Following me? Okay, so we're using this formula now. They are gases. They're at STP, so you can use the 22,4, and we just divide quickly. 0,5 divided by 22.4, and we land up with 0,022. Okay, it's okay, you can do that, it's fine. All right, and that's your number of moles of oxygen gas under these conditions. All right, I hope this makes sense to you. So just one thing though, the textbook, you must just be careful if the textbook doesn't mention that. Sometimes textbooks, they forget to put STP, and then you left going, but there's nothing else you can use. So if the textbook, I haven't really looked at the exercises for this, if you see that they're leaving out the STP, then assume STP. But in an exam, you never assume I will give you STP or not. Okay. Calculate the volume of 32 grams of ammonia gas that a gas occupies at STP. What are we going to do? When in doubt, mole it out. So let's write down what I've got. Okay, we've got that. It also said ammonia. Ammonia is NH3. Okay, so let me just look at my periodic table. Okay, so the molar mass of NH3, nitrogen is 14 plus 3, so we get 17 grams per mole. Okay, we're going to work out our number of moles. Why? Because at the end of the day, we want a volume. So let's just see which one will give us a volume. We know that this equation will give us a volume. So I've got that because it says STP, but I need this so that I can work out that. All right, so that's why we're working out moles. So mass over molar mass, 32 divided by 17. I probably should know this, but I'm tired. Okay, so 1,88. Okay, 1,88 moles. So now we can put it in this formula and get the volume. So 1,88 is equal to the volume over molar volume, which is 22,4. We can use it because it says STP. So 1,88 times 22.4. Because remember, you're going to bring that up there. And our volume is equal to 42,11 decimeters cubed. Okay, right, and that is that. I hope you understand. Please let me know if you don't, and we can do a Google Meet. All right, have a good day.